has to change signs as you're moving across A. And that's what's going to give us a point of inflection. To expand on point of inflection a little bit, so we have point of inflection, some other ways I'll call that POI, pretty common abbreviation. Inflection point, same meaning. That third one you see with the X, that's just the British English spelling of point of inflection. So if like you're looking at stuff online, if you see that, it's all talking about the same thing. The way I think about a point of inflection is it is going to be the place on the graph where f of x changes concavity. And so when we're talking about where it changes concavity, it's going to be where it changes from like concave up to concave down. I think an easy way to imagine this, if you just think about like the classic, parent function of a cubic graph, you can see there is some instance on the graph that's a coordinate that is going to represent the point of inflection. It's basically where the graph in this case is changing from being concave down, if I can do things correctly, to concave up. So it is going to be an actual point on the graph. So that is something I do want to make clear. Just because the concavity changes doesn't necessarily mean you have a point of inflection. For example, if it changes from concave up to concave down across an asymptote, that asymptote is not technically a point of inflection because it's not a point on the graph. So if I'm talking about a point of inflection in regards to the second derivative, again, it's where f double prime changes signs. And that is important to make a note of because oftentimes when you're asked to justify that something is a point of inflection, as we'll see in our example today, we're basically just going to justify and say like, oh, the second derivative changes from positive to negative or changes from negative to positive. So to look at the example that I have, I'm not going to look at a graph first since we did kind of do that with intervals of increasing and decreasing. But I have find the x coordinates at which the graph is neither concave up nor concave down. When I'm looking for where this graph is neither concave up nor concave down, we know that that means we're finding where that second derivative is equal to 0. I know for the first derivative, we would call that those like critical points. And critical points are when the first derivative is equal to 0 or undefined. There's not really a special name for where that happens on the second derivative. So you'll often just hear me call it like important points on the second derivative. So since we're dealing with intervals of concavity, we do need to find that second derivative. Of course, to find the second derivative, you do need to find the first derivative. This one, you could use the quotient rule. But when I see this one, I see that this one is pretty easy to bring that denominator up with a negative exponent. And in fact, that's the way I'm going to recommend you do it. Because if you have to find the second derivative, you do not want to have a messy looking first derivative. So there's my y function rewritten. So I'm going to use the chain rule. That -1 comes down in front. 6 is a constant multiple coefficient. The inside stays the same. The new exponent, -1 minus 1 is -2, and then don't forget about the good old chain rule. And then before I find the second derivative, it is helpful to simplify your first derivative. So like -6 and 2 makes -12. There's an x, and then I have x squared plus 3 to the -2. So that is my first derivative. If I was wanting to find intervals of increasing and decreasing, this is what I would use to find my intervals of increasing and decreasing. But we want to find eventually the intervals of concavity. Right now we're talking about where the graph is neither concave up nor concave down. So we do need to find this second derivative and then simplify. And that's really where most of the algebra is going to come into play. So if I'm finding my second derivative, I am going to have to use the product rule because there's x's in both of those being multiplied. It's not a constant multiple. So if I'm taking the derivative, so I have like the derivative of -12x, which is just -12. Then I have the second piece that I can bring across. And then I can take the first piece times the derivative of the second. So that -2 comes down, x squared plus 3 stays the same, new exponent's -3. Don't forget that chain rule, times 2x. Of course, this is the product rule, so that order doesn't matter. You could have those two terms completely flipped around. And then this is where like your good algebra skills are going to come into play. So like we want to find when this is equal to 0. And right now, I hope you look at that, and that's definitely not an equation that you want to solve. Since it did come from the product rule and derivative, they usually simplify almost the same way every time. So I am going to go ahead and clean it up a little bit. So this first term is this negative 12 x squared plus 3 to the negative 2. This second term, I have like a negative 12, a negative 2, and a positive 2. So that becomes positive 48. X and x makes x squared. And then I have the x squared plus 3 to the negative 3. Still not the nicest thing to solve. Again, we want to find when this second derivative is equal to 0. So at this point, this is where I do, again, the very mathematical sounding fancy factoring that we did a little bit of last year, where you're basically pulling out the greatest common factor from that. So if I'm looking for the greatest common factor, I definitely will look at kind of the easiest parts of that first. So I have like the negative 12 and the 48x squared and look for that common GCF from there. And the only thing that that really has in common is a 12. And then I'm going to have what's left over on the inside. In that first term, I have a negative 1 left over. In that second term, we have an x squared left over. We took out the 12, so 12 times 4 gave me the 48. Then I want to factor out the binomials. So they both have this x squared plus 3, but one is to the negative 2. The other one is to the negative 3. And I just want to remind you, like if you just think about regular factoring out the GCF, if I have like x squared plus x cubed, the GCF is always the smallest exponent that they have in common, and that's what you can end up factoring out. It works the same way even if your exponents are negative, so I see that the negative 3 right here is the smallest, so that actually is my GCF factor that I can pull out. When I factor it out, I have to kind of see what's left over. So in this first term, we have a negative 2, so think about your properties of exponents. You add exponents when you multiply. So negative 3 plus something is giving us that negative 2, which is 1. And a little bit of a hint, like it's always going to be 1 because this did come from taking the derivative where we always subtracted by 1, so it's always just going to work out nicely like that. And then we took out from that second term all of the x squared plus 3. So now we can go ahead and just like simplify this again because we do want to solve it. Similar to what we did yesterday, if we are going to have to eventually make a sign chart, having it factored and as a single fraction is going to be your best way to approach it. So if I'm just looking at this part in the brackets, like distributing that negative 1, x squared minus 3 plus 4x squared. So I have a 3x squared minus 3. And then that becomes pretty easy to factor out. And then I can kind of pull all this together to find like a nice, clean, simplified second derivative. So I have my second derivative is equal to, there is an x squared plus 3 to the third in the denominator. I have a 12 and a 3 in the numerator, so 36, and then the factors of x minus 1 and x plus 1. So when I'm looking for where this problem is neither concave up nor concave down, again, that's when the second derivative is equal to 0. The second derivative is equal to 0 at 1 and negative 1. I don't know where I got that 2 from right there. Definitely should be x plus 1. And so I see that my key points, again, these aren't called critical points because they came from the second derivative, but those are just some like important points on the graph of that problem. So there is a lot of algebra, and we know there's going to be a lot of algebra when you have to find first the first derivative and then the second derivative. Before I go back and move into the intervals of concavity, does anyone have any questions on my steps for that problem? All right. So the next part I want to look at, I'm going to use that same problem so we don't have to redo that algebra, is I want to talk about how we can find the intervals of concavity, like where's this graph concave up and where is it concave down. Similar to how you did intervals of increasing and decreasing, you first want to find some important values on the second derivative. So you basically want to find when the second derivative is equal to 0 and where the second derivative is undefined. I put that in parentheses because like that's kind of like a weird area we get to when we talk about concavity. Because technically when the second derivative is undefined, it probably means that like the first derivative is undefined there, or maybe the graph itself is undefined there, so there's not actually a point there. But it is still going to be an important part on the graph. And then basically once you find those important values, you're going to make a sign chart. But instead of making a sign chart with the first derivative, you're going to make a sign chart with the second derivative. So I'm not going to do all that work that we just did again. I'm just going to kind of bring across what we found. So we already found the second derivative, which was this. And then we also have our important points. We saw that we had one at -1 and +1. We would also want to go ahead and check the denominator, but if you're looking at that denominator setting it equal to 0, you would get like x squared is equal to -3, which is non-real, so it doesn't give us any key value. So we only need to worry about using -1 and 1 on our sign chart. The sign charts are going to be something you should get used to, like we'll do them a lot in calculus, not just in this unit, but outside of this unit as well. So again, remember when you're making a sign chart, I designed mine so I have a number line and I put my key values here. Again, these are not critical points because they came from the second derivative. And then in the column, I just list all my factors. Some people do choose to leave off like the 36 because you know it's already always positive. Again, I like putting it there just so I can kind of clearly see everything that makes up my second derivative. And then if you put little vertical bars underneath the key values and the factor they're associated with, because we know it only can change signs on either side of that vertical bar. And then I just want to start filling it in whether it's positive or negative. Some parts of this is going to be really easy, like 36, no matter what you do to it, it is always positive. Same thing for that last factor, x squared plus 3 cubed. Yes, something cubed can be positive or negative, but if I square a number and then add something to it, well, squared number is already positive. A positive plus a positive is still positive. So this bottom row is also always positive. And then we can kind of fill in the signs for the x plus 1 and x minus 1. To the left of -1, just think of a number like -2. -2 plus 1 is negative. Anything bigger than -1 added to 1 is going to give you a positive number, like 0 plus 1 is positive. And then for x minus 1, we have something similar. To the left of 1, that factor is negative, and to the right of 1, it's positive. Then you want to figure out what the second derivative is overall. So in this first one, we have 2 positives and 2 negatives. 2 negatives make a positive. In the middle column, we only have 1 negative, so the whole column is negative. And then for this last one, everything is positive, so we know that that interval is positive. Remember that a sign chart is not your answer. You just use it to kind of form your answer. So if I wanted to talk about the intervals of concavity for this one, we have my function y is concave up on the interval from -infinity to -1, union 1 to infinity. How do we know it's concave up there? Because the second derivative is greater than 0.
You're not sharing your screen.
Say it again.
You're not sharing your screen anymore.
Oh, I'm not? That's awkward. Let me try that again. I back? Maybe?
Yeah.
Okay, that was weird. I don't know what happened. So I have my function will be concave up when that second derivative is positive, and I know that y is concave down on the interval where the second derivative is negative. And again, if it asks you to justify your answer, you would want to make sure you do have that because statement. It seems like a lot of writing, but at least it's not as much writing as you would have in AP Stats. Questions on how I found those intervals of concavity. All right, so I did, we'll do all this without a calculator, but I did go ahead and graph it just so you can kind of see where the answer comes from or what it looks like. So in a normal 57-minute period, I would have done a warm-up where you found the intervals of increasing and decreasing. To save time, I took that out, but I did go ahead and include it on here. But you can see the concavity that we found, basically -1 and 1 are kind of the dividing points for concavity. And we can see that it is concave up on kind of the edges of the graph and concave down in the middle. One thing I do want you to add to your notes is really this very last bullet point I have typed in, if anything, and that's how you justify a point of inflection. So for points of inflection, we do have two of them. We can see them. We have points of inflection at -1 and +1. Going back to the sign chart, I know that I have points of inflection because we can see that as we cross over -1 and 1, the sign of the second derivative changes. So for example, if your sign chart went like positive, positive, then negative, that point that was on either side of positive would not be considered a point of inflection. So when you're justifying a point of inflection, we're not going to make it complicated. So we identify them. We know they're points of inflection because y double prime changes signs. You can be real specific and say because y double prime changes from negative to positive or positive to negative. But if you just say changes sign, then of course you're going to include all the possible instances where that happens. Questions so far? All right, so yesterday I ended with a trig problem. I did want to go ahead and end with another trig problem today. I'm going to let you try this one first before I just jump into it. So I give you a function. Make sure you notice that is x times the cosine of x. So use the proper rule when you do that first. When I give you trig, I will always have to give you an interval. Since trig is periodic, you want to have some sort of interval to talk about either increasing or decreasing or the concavity. I am going to give you some time to try this on your own. Probably not all the time you need, but I do want to give you a chance to get started on it. So if you're asked to find intervals of concavity, you know the first thing you need to find is the second derivative. And again, I do recommend after you find the first derivative to simplify it first before you find the second. And then just make sure you're careful with your rules here. You should be using the product rule, and then just be careful with your signs for the derivative of sine and cosine. We know that the derivative of cosine is negative sine. But take a moment to try those before I start kind of working it out and going over it. So if you're looking at my work, so I went ahead and found the first derivative. Thankfully, we're not talking about intervals of increasing and decreasing because this would be a really gross first derivative to try to solve. So we have the product rule for that first term, and then -2 is just a constant multiple. The derivative of sine is just cosine. If I have one cosine and I take away two cosines, that's going to give me minus cosine for the second term. So this is my simplified first derivative. Since I'm doing concavity, I need the second derivative. So I use the product rule again. Make sure you're careful here. The derivative of cosine is negative sine, so that last term becomes plus sine. Negative sine and positive sine cancel out. So your second derivative is just negative x times the cosine of x. So now we need to find our important values for the second derivative. Again, these are not called critical points. Those are only associated with the first derivative. So we want to figure out when this is equal to 0 or undefined. This one, there is no denominator, so like it's never undefined, only can be equal to 0. Even though this doesn't look like it's been factored, like those are two factors, they are two things multiplied together. Since we have two things multiplied together equal to 0, I can just set each factor equal to 0. So I get x is equal to 0 as one key value. And then you do want to be careful with the trig. So I know that cosine is equal to 0 at pi over 2 and 3 pi over 2. But the interval for this problem is looking at negative pi to pi. So if you're thinking about the unit circle, instead of going from 0 to 2 pi, we're going back to negative pi and then forwards to positive pi. So we want to make sure that we choose angles that match that. So instead of saying 3 pi over 2, we're choosing negative pi over 2. So I created my sign chart. Again, this one has intervals on it, so I kind of put the negative pi and pi on there. And then I just want to figure out when is it positive and when is it negative. When I say it, I'm talking, of course, about the second derivative. So for negative x, we know that when you plug in a negative number in for x, that becomes positive. Plugging in a positive number is going to stay negative. And then for cosine, this one's a lot easier than the one we did yesterday because you can just think about the unit circle of when cosine is positive and when cosine is negative. From negative pi to negative pi over 2, that's quadrant 3, cosine is negative. From negative pi over 2 to pi over 2, that is the right half of the circle, cosine is positive. And then from pi over 2 to pi, quadrant 2, cosine is negative. So what is your second derivative doing overall? We have a negative interval, a positive interval, a negative one, and then a positive one. I do want to justify my answers and clearly state what these intervals are. Again, the sign chart is not where you're done. You're just going to use that to answer the question. So I know that this graph of y is going to be concave down and concave up. I'll do concave up first. Is concave up when you are from negative pi over 2 to 0, and from pi over 2 to pi, we'll always use parentheses. I know it's concave up because the second derivative is positive. I know that y is concave down on the intervals from negative pi to negative pi over 2, union 0 to pi over 2. How do I know it's concave down there? Because the second derivative is less than 0. The instructions tell me to find the x and y coordinates. I'm going to edit it because I'm the teacher and can, and we're just going to find the x coordinates of any point of inflection. Again, it's only officially a point of inflection if the second derivative changes signs. This one, we notice it changes from negative to positive and then positive to negative at every interval. So all those points are going to end up being points of inflection. So my points of inflection are negative pi over 2, 0, and pi over 2. They are points of inflection on the graph of f of x or y. I guess I can name it what I called it. And how do I know that they are points of inflection? I know that they are points of inflection because the second derivative changes sign. Again, a common mistake people answer is they'll say that those are points of inflection because y double prime is equal to 0. That isn't what makes them points of inflection. They are points of inflection because that is where the second derivative changes signs. Whew, I just did a lot of talking, but any questions on that problem?
So if the signs didn't flip-flop like that, the x coordinates wouldn't be points of inflection, but would the concavity still be valid?
It will still be concave. So like if I just made up an example, like completely just making up an example, and I had those as my key values, and in my second derivative, we say it went from positive, positive, negative, and then positive. Like your graph would still be concave up from like negative infinity to 1, and then from 1 to 2. But the only points of inflection you would have would be at 2 and 3. Because those are going to be the only places where the concavity is changing on the graph.
Oh, well.
Does that answer your question, I think?
Yeah.
Okay. And yeah, that's a good question. So most of the time, just by the nature of these problems, like it's going to switch back and forth. There's a few, especially when we have like lots of polynomials dealing with like different multiplicities. Sometimes you'll have sign charts that end up looking like that. So your assignment for today is to work on homework. So I assigned homework 1 yesterday, dealing with intervals of increasing and decreasing. I'm assigning homework 2 tonight. Please note that that's multiples of 4, so it's really not that many problems once you get started. And some of those actually have pretty easy second derivatives to find. Wednesday, you know, is asynchronous. Just for us to stay on track, I am assigning something for this Wednesday that I need for you to watch. And I am assigning for you to watch a video that I created on relative extrema. It's only 10 minutes, and then there is a homework 3 that's attached to it. Thursday and Friday of this week, we are going to kind of mix all of those topics together. So like I'll still do relative extrema notes on Thursday and then Friday. But I really do need you to kind of like preview it beforehand, just so that we can kind of focus on like the calculus and you can review the notes beforehand. It's pretty easy. Like there's 2 tests we'll look for extrema. The easiest one I can tell you, like, it's pretty basic. Like if we know the graph goes from increasing to decreasing, then we know we have a maximum. If we know the graph is going from decreasing to increasing, we know we have some type of minimum. So there is like some common sense stuff in there, but it is something I'm assigning. It will be posted in Teams in 2 places, on the general channel and then also in assignments. I will also send out the link to the video via Remind tomorrow, but you will have to log into your Microsoft account to view it. So that's kind of what you're working on. Like I know that feels like a lot, but we will have class time and stuff to work on it Thursday and Friday. At this point, if you're good to go, you can go ahead and sign out of this meeting. Office hours are all day tomorrow, so if you do want to meet with me during office